the graduate program for hydrologic sciences. And then I did, I graduated quite a few students, but just a few from GPHS. Um, and there's a gathering of alumni coming up that I intend to be at. There's also a um, a uh, a social tonight, and there will be Martha Breedemeyer uh, Allison Starr will be at that tonight. So I'm not sure whether I will be yet, but if anything catches your attention in my presentation today, you'll be welcome to talk with them, and we can take this further for your organization. Um, and now, after teaching for 32 years at UNR, I retired, and really the best way to kind of bring the technologies that I was working on at the time is to start Terēan and bring those technologies directly to practitioners all around the world. Um, so we started Terēan in 2023, and uh, we have customers, hundreds of customers all around the world. Most of them are geotechnical engineers, and I will explain that. Um, and we are also working with many agencies, from the Department of Energy and the USGS on down through all the, some local agencies as well. Um, so that's a right now kind of a supplement to our basic business serving geotechnical engineers. So I'll explain how that all kind of fits together. Now, you're welcome to interrupt me during my webinar if you have urgent questions. If I've not been clear about anything I'm saying, I'd like to be I'd like to have the chance to clarify it. Happens all the time, and now I may not notice you trying to speak up. So Tina's given you several methods, and I've let Tina know that I'd be happy if she came on screen and interrupted me when if that becomes necessary. My intention here is to present for 40 minutes, and so that we can have plenty of time for questions afterwards, or you can leave and finish your lunch, however that works out best for you. Be glad to get questions about this or anything else Terēan's doing at any time. And you've got my email here on this slide and in the announcement. Okay, so now all right. What I'm going to talk about today is probing aquifer geometry and structure to thousands of feet depth with seismic surveys that only take one day. Okay. Now, this is really a new application for Terēan, as for many people who do the kind of seismic surveying that we do. So I'm gonna review a little bit first the what is refraction microtremor surveying, and how is it what's its role in very shallow studies, critical zone studies. Some of you may be involved in those. Also, where the bulk of Terēan's business is right now, geotechnical engineering. Also, the location of faults in the shallow subsurface, by which I mean less than 100 meters depth. And also, even at less than 30 meters depth for excavation and drilling and excavation planning. And then I'm going to talk a little bit about the field work for Terēan's brand of refraction microtremor, which is called REMI. REMI recording and analysis is what is a lot of what Terēan does. We do other things too. We do other kinds of seismic surveys, other kinds of geological and geophysical investigations. But the backbone of our business now is shallow and deep REMI. So then, with that setup, I'm going to then apply and show you what some earlier work on investigations of Reno area basins and aquifers. First by UNR, and then by the UNR and the University of Cincinnati. A lot of that early work was sponsored by the U.S. Geological Survey as an earthquake hazard reduction project. And now Terēan is undertaking a lot of these surveys, often in concert with UNR and the University of Cincinnati. My colleague Dan Sturmer at Cincinnati. We'll talk a bit about investigations of bedrock aquifers in Nevada, still fairly deep, and then thanks to it's been great doing a project with the Truckee Meadows Water Authority and the folks there. And I'm going to show you some results of our investigations with TUMWA of aquifers in South Reno for a water supply well re-drilling project. So that's where I'll end. That's where we're going. And I think we would like to do a whole lot more of these projects. Okay, so a lot of our work for the geotechnical industry has been based on standards. And the most recent standards have come from the USGS and what's called the Consortium of Organizations for Strong Motion Observation Systems. That's an organization called Cosmos. And they, of course, work in earthquake hazard. And this really came from the USGS's efforts in measuring and mitigating earthquake hazards around the country. They published an issue of the Journal of Seismology that has a large number of peer-reviewed papers about various surface wave methods of probing the subsurface, usually the shallow subsurface for earthquake hazard purposes. And a couple of the papers in there have to do with REMI. The REMI guidelines paper, which explains all about where REMI's been applied, and it includes both shallow and deep applications of this surface wave geophysical measurement technique. And it's really this paper is really a manual for what you can do and how to do it. Okay, so that's an open access paper in the Journal of Seismology, and you can also get this issue, and all the papers are open access, and you can see how it fits in, how REMI fits into all the other surface wave techniques. Now, really, the essence of our of what REMI is being used for, today, tomorrow, yesterday, all around the world, is these profiles of depth to shallow bedrock. This is an engineer in Guadalajara who used our Terēan software, or Terēan REMI software, and some, fairly common equipment that Terēan also can set you up with to get the depth and thickness of layers and the bedrock topography. And you can see, if you can read the scale on the left, this is a cross section. We're looking at about 50 meters across the top, and from depth extending from the surface down to 30 meters. And what we result in is this cross section of the shear wave velocity property of the rocks and soil. Okay, that shear wave velocity property is linked pretty closely. There are some complications, of course, but pretty closely to the bulk shear modulus of the rocks. Although the shear wave velocity can vary by a factor of 100 in common soils and rocks, whereas the modulus, as I'm sure you know, can vary by by orders of magnitude in different materials. So the higher modulus, higher shear wave velocity rocks in this section are in the warmer colors, topping out at almost 600 meters per second. That's the one of the common ways of denoting the shear wave velocity. And you'll notice at the surface, as geologists certainly would expect, you have the looser, weaker, more jelly-like materials at the surface, and those are in purples and blues. Okay, those will have velocities below 300 meters per second. So not a huge range in this section, but a very important one, as the 300 meters per second velocity soils and rocks are easy to excavate, or rippable, as they would say. And when you get up towards the 600 meter per second velocities, those are in this area. They're in basalts, and they may not be rippable. Okay, so right here we're getting some excavation and foundation design guidelines that's why this engineer did this survey. Here's another example of construction and excavation planning based on a 2D REMI survey. We're looking at another cross section again. High velocities are warm colors, and low velocities are cool colors. And now this is done by an engineering consultant in Utah, and they're planning a trail for a Utah state park. So before they start constructing the trail, they want to get the rippability, so they know where the trail is going to have a good foundation, and where there is soft material that they may want or have to remove, and also could not prove a good foundation for piers. Okay, so the hot colors are not rippable. The cool colors are rippable. Green is kind of in between. It's marginally rippable, and you've got the velocities in thousands of feet per second there. And this this trail was built shortly after the survey. And the survey was done on spec, basically, before any other work was done. And in the excavations and drilling that they did in the construction of the trail, they did find that pretty much what they saw, this marginally rippable area that is on the left. They moved the trail over the beginning of the trail over a little bit to avoid that sort of marginally harder rock area, and they could lay down more easily a good trail bed. Now, this is a very interesting project that happened just a couple of months ago. One of our clients was working a property that crosses the Calaveras Fault in Pleasanton, California. As you know, the Calaveras Fault is a segment of the San Andreas system. Very, very active, very, very dangerous in California. You have to locate the fault and stay away from it when you build something, or you get an engineer to design your $10 million building with $1 million worth of design work. That's been done too. So locating the fault is key, and with a Terēan REMI survey that was that could cross the fault. The REMI survey itself was 230 feet long, and resulted in the cross section at the lower right, which goes down. You can see about 50 feet. You can see the topography in white at the top. The white is air, and the topographic surface is where the color begins. Again, the stiffer rocks are red, and the softer rocks are blue, soils, as it were, since they're all pretty close to the surface. And the entire survey, and really a lot of the analysis, took just a total of 30 minutes. So they put down the 24-channel geophone array. They recorded data for 15 minutes, and they took it up, did some hammer hits along the way as instructed by the standards documents. And they got this result where there's a clear lateral discontinuity in velocity. Velocity changes by a factor of 1.5. By more than 50% across at 20, 30 feet depth. And you can see there's this very low velocity, very blue soil layer at the top right that starts at the fault. So the fault could be located to an accuracy of 10 feet here, whereas before they really, the Alquist-Priolo zone was 100 feet wide. And it only took 30 minutes in the field. Now, this opens the possibility, faults, of course, they can be groundwater conduits, they can be groundwater barriers. Locating those faults, especially shallow, can be quite important to many projects. And, these techniques are being used right now for those purposes. We have lots of clients locating faults for these reasons. And I want to talk, about aquifers, and they're deeper than 50 feet generally. So what we have is early results, that sort of tested REMI against a bunch of other techniques, and borehole logs included. They extended to more than 100 meters depth. So it's good to remind people that really the what I'm calling deep REMI is not anything so new. This is a result published by the USGS in a seismological bulletin, back 20 years ago. Here's another result published not quite 20 years ago, again in the seismological bulletin in the deep Los Angeles basin. showing REMI results versus a suspension logger in a borehole down to more than 200 meters depth. So this is really nothing new. So what that got us doing was considering places like Reno. Okay, and here's a map of Reno. You can see maybe the trace of the Truckee River as far east as downtown, and you can see a bit of the Sparks Marina up there in the top half of the map, and you can see the Steamboat Hills and South Reno down in the south. And these red marks are, again, we were considering it first for earthquake hazard assessments. These are traces of the Mount Rose Fault Zone, very complex, very very poorly known. There are places like this yellow triangle where there has been trenching of the fault zone, so a little bit more is known there. Um, and a lot of my colleagues think that the next likely earthquake that'll be right in Reno, I can't tell you when it'll happen, but they think that this is the very likely earthquake that will, perhaps be one of the next to happen. Um, it'll be on a fault a rupture surface that projects to the surface on this red box. It could have an epicenter under the Steamboat Hills at the Green Star, and it would be a magnitude of about 6.3. So, we've been studying the Reno Basin. Formerly, it ought to be the Truckee Meadows Basin, right? So I call it the Reno Area Basin, from Verdi on the west to the sewer plant on the east side of it, where the Truckee River exits the basin, and then all the way down to the Steamboat Hills in the south. We've been studying it for a couple of decades now, and we realized, that maybe we could add some information. The information on the basins here, we're focusing in on the Reno and the Sparks subbasins. We're not really looking south to South Reno, and we've got in A the map from gravity structure that appeared that the USGS came out with in 1995, and then a geophysics student and I added to that in 2001. We sharpened up the structure a little bit and saw that it was deeper than maybe we thought. The Reno Basin is perhaps a little bit more than 1 kilometer deep, 3,000, a little bit more than 3,000 feet deep, over below about West McCarran and Mayberry Drive, if you're familiar with Reno. And then one of Tumwa's predecessors, the Washoe County Water Resources Department, did further gravity surveys, and some of that was published in 2012. Mike Widmer was one of the real movers of that effort. They detailed the basin thickness in Verdi, and also in West Reno, and you essentially have a very similar model in Sparks to the 2001 work. So we said, all right, we know the Reno Basin pretty well. Let's come through and get the shear wave velocity in it, which makes a big difference to the earthquake hazard, and see if we can verify the depths that the gravity is getting. Okay, so we've had at the university we had a multi-year program from 2012, 2013, 2015. We had USGS sponsorship of deep REMI surveys. and also I had a class do a project in 2016. The objective of these surveys was characterization of the basin for earthquake resilience assessment and planning. Now, all of these surveys, you can see 2012 was the original surveys and they're on the west side, kind of between Mogul and central Reno. So they're assessing the deep part of the West Reno Basin, under West McCarran and Mayberry Drive. There's 3 lines there. Each line took 1 day to do. Okay, it involves setting out instruments, and here's some pictures on the left of students and faculty. This is Dan Sturmer from Cincinnati. They're doing a survey just a couple of years ago, but the 2012 through 2016 surveys were very, very similar. And then in the middle, the middle pictures are the equipment that we used with Tumwa earlier this year. And this is a cabled system, unlike the independent seismometers we used for the earlier surveys. And this system, maybe it could see all the way down to the bottom of the basin, but that would be dicey. But, for West Reno at 1 kilometer deep, but for less than 1 kilometer deep, this cabled system worked very, very well. This is, you can see the data collection box, which has Wi-Fi to a laptop. So you can sit in the air conditioning or or out of the rain if you have to, out of the wind, while the data collection box does its thing outside. And you can see on the right just a view of one of these deployments that we did with Tumwa. Again, each survey, a couple of kilometers long, kilometer to 6 kilometers long, basically takes 1 day. Maybe less in the case of the Tumwa surveys. So here's the results that were published by Asha Pancha in 2017. Pancha works for Terēan now, so we're very happy about that. These surveys basically got cross sections of velocity, shear wave velocity. Again, the cool colors are the softer material, the basin fill. The warmer colors are the bedrock. You can see that about 500 meters depth in a lot of these basins, or if the basin is not as deep as 1 kilometer, it could be a shallower depth. We transitioned to a bit of a stiffer basin fill in green, and then into the andesite bedrock, volcanic basin fill bedrock, which is much higher velocity in red. So particularly it was line 2 here, the north-south line, where we could see the basin depth of 1,000 meters, 3,000 feet. So these took 3 to 4, 1 day per array, 3 to 4 hours of recording. My seismology colleagues asked me, so where does the seismic energy come from? It comes from the urban environment, trains, planes, traffic. It can also come from wind and trees shaking in the wind. The wind impacting against the hillsides. All of that generates the sort of background seismic energy that we use. Okay, here's a comparison of the black line is kind of in earthquake hazard parlance the Z1.5, where the shear wave velocity gets high enough for it to be considered engineering rock, at least in some cases. And the gray lines are where the different varieties of the gravity, from Widmer's on the top in darker gray to the 2001 UNR product on the left. You can see the gravity doesn't quite agree, and the deep Remy kind of says, well, both are right in certain places. Here's just an example of one of the later surveys that's actually not in Poncha's 2015 publication, but it's in reports you can download from the U.S. Geological Survey. So it's kind of poorly published in that sense. We can see the fault that defines probably a tertiary fault that defines the east edge of the West Reno subbasin. So we were able to track that, offsetting the high velocity red bedrock down to 500 meters depth. So if there are those who are curious about how deep you can go, there's several rules of thumb. Really a basic design principle we use is the middle one. We can see down to half of the subarray length, and the subarray length is going to be half of the whole array length. So when we put out a 6 kilometer long array of seismometers and we take 3 kilometer subarrays, that means we can see down to a maximum of 1.5 kilometers, which for Reno works. Okay. So also we can assess the velocity of the basin fill. These are all the different profiles, averaged together. And of course, there is variation laterally, as well as vertically in these basins. So we have an assessment of that. Here's the attempt to look deeper with very long surveys. I think we ran up against the capabilities of our instrumentation. We could see down 2.5, 3 kilometers. Maybe we could see the bottom of the volcanics in some areas. So that's what those 2016 surveys were good for. Just some more illustrations. In 2021, Cincinnati and UNR did a collaborative experiment where we assessed the basin fill. So the basin fill, of course, controls the aquifers. So we had areas of the west side of Washoe Valley where the Slide Mountain slide had impacted both in, back in the 80s and in the geologic past. And then an area, line 2 down here, the red line 2 is south, where there haven't been any slides. At least we see nothing on the mountain front to indicate that there have been any major slides. So we have the slide profile of the basin and the no slide profile of the Washoe Valley basin. Washoe Valley itself is up to 250 meters thick, the basin fill. And if you think about, we've got in the slide area, we've got, these probably early quaternary or late tertiary accumulations of very blocky slide deposits. Those are providing high velocities in the middle of the basin with a velocity inversion and softer, more porous materials down below. So, you would think that the aquifers would also be divide themselves in this way, whereas we don't see those blocky slide deposits in the southern survey where there have been no slides, at least we think. So there's no, that doesn't mean there can't be artesian aquifers, which of course there were there. It just means that there's there's no indication of slide deposits. So more lately, UNR and Terēan and Cincinnati profiled the industrial basins north of Reno and east of Reno, in Reno Stead and the Tahoe Reno Industrial Center, TRIC as I might call it. Here's a profile, a deep REMI profile from there, from the red outlined north-south profile. We're looking, we see a basin about 700 meters deep. And there's lots of other information in these areas. So, we improved the gravity measurements there as well. We did another essentially seismic technique called HVSR. And it's interesting how that the HVSR really agrees with the deep REMI on the high velocity transitions. The bottom of both the volcanic and the sedimentary basins, whereas the gravity will go up to the top of the volcanic part of the basin and agree with that. So that's a kind of an interesting contrast. Now we get to some recent work. I'm not going to tell you where this is or who got it, but this is work locating faulting of basin margins, and you can see down to depths of 400 meters, maybe more. Again, the stiffer materials are warm colors. The softer materials are cool colors, and the fault offsets in the both volcanic and Mesozoic stratigraphy are quite clear, and sometimes they agree with where faults were projected originally by geologists, and sometimes not. And the drilling that's been done on these in these areas has tended to confirm what the deep REMI sections do say. Okay, so now we come to the Tumwa project, which we're very very excited about and very pleased with the results. They have a couple of existing wells that they want to re-drill, and before they re-drill, and in this area of South Reno, there's lots of possible faults, at least that are marked on maps. How many of them are real, and how many of them offset or restrict or could cause a barrier within the aquifers. All of that is kind of up for grabs, and we need some real profiling. So these cross sections extend to I think that looks like 300 meters depth. I believe this is probably well, no, actually, this is this is 1,200 feet. Okay, of 1,200 feet of elevation difference on the depth scale, and it's a 2,000 plus, a little bit more than 2,000 foot long section, cross section here. And so what we can see are the various layers of more a little bit stiffer and a little bit softer alluvium and fluvial deposits, going into a little bit more compacted tertiary alluvium. That would be D. Okay. And then a mysterious formation E. You'll notice that wasn't in green. That wasn't intersected by the existing well. So we speculate, that could be fractured volcanics. It could be tertiary gravels. It could be diatomite. There's lots of speculation about that, and then finally into the Cape Peak andesite bedrock F in dark red. Okay, and what we've noticed is that over here on the left side of it, there's a thicker aquifer, Okay, now that's outside these vertical lines, which are, kind of the easier places to get permits to drill. Um, and so now, given this information, Tumwa has some real, information to be able to plan the well redrilling. Considering all the factors, is that thicker aquifer worth the trouble to go to? Um, Maybe it's not. And at least there's places where we wouldn't want to redrill because the aquifer in the main aquifer in blue is not quite as thick as it is at the existing well. Um, the work that the Tumwa people did early on, and to assess this existing well, you can see that it turned out they put it in the right place. Okay, so these results make the re-drilling planning a lot more certain and remove a lot of the uncertainty that can uncertainty always makes things more expensive, and that's what we're about is helping agencies and companies make their developments more certain and less expensive. You can see that here in green, we in the layer C, we picked up at this other existing well, we picked up the a gravel, which is seen in the well log, and here the well did reach the volcanics, and we confirmed that. Um, and there's some potential faults. We're not sure we see them either in the bedrock or in the stratigraphy above, as far as we've been able to assess it. Um, so those are interesting. We're not sure we see any sign of the fault on the map. Is that even in the right place? If you go and ask the USGS, who put it in their database, in their fault database, they're not sure either. But seeing this gravel extending and thickening to the right was very encouraging. Okay, so I have, of course, taken longer than I thought I would, but thank you for your attention. Um, and let me just summarize that the deep REMI technique here is really using the same Terēan technologies as the geotechnical industry is using for shear wave site class. If you've heard about VS30 and construction and getting building permits and all that, and it's the same thing that we do for shallow imaging. All we've done is really extend the REMI arrays to kilometer type lengths. We record instead of for 15 minutes, we record for a few hours. And we can get velocity structure to 1 kilometer depth. Okay. We'd like to try some deeper basins, and that'll take some a little bit more complicated technology, but the technique certainly will scale. But of course, a lot of aquifers in Nevada are within 1 kilometer of the surface. So deep REMI assesses basin stratigraphy and aquifer thickness, and it has the potential for locating fault barriers and conduits. So that's my summary, and I'd be happy to take questions. And okay, so I've got one hand raised. If Michael, you're able to unmute yourself, or maybe I can unmute you.
I am. helping with that as well.
Okay, thank you.
And I'm sorry, I tried to unmute my video when you were speaking to give you the 30-minute heads up, but you were busy.
Yeah, yeah. Thank you, Tina, though. I appreciate that.
Yep.
You tried.
Okay, Michael, are you able to unmute yourself?
Yeah, I'm unmuted. I think, can you hear me?
Perfect. Yep,
Yes,
perfect.
thank you,
Thank
Michael.
you.
Yeah, I was just wondering, can you see rock type contrasts in the basement rocks? Like, could you see the difference between an intrusion versus volcanics versus Ordovician metasediments?
Yes, and we're seeing that uh, in those basin margin surveys that I was showing you, at least down to let's see, the elevations in yeah, at least down to 200-300 meters depth. We're able to distinguish the some of the details of the complex stratigraphy and thrust sheets that make up certainly a lot of Nevada. Um, now, one thing that we are relying on a lot is that I well, I wouldn't expect there to be much difference in velocity between, say, a Mesozoic granite and a Paleozoic um, metavolcanic or a Paleozoic sandstone. Those may be very close in velocity. Um, but still, wherever there are boundaries, if they're offset by faults, then at least we can locate the faults and start to build a structural model that way, and then that can help you trace your rock types from a boring, say, to across the cross section. Then,
Have you used this for any mineral exploration programs?
um, I'm not going to confirm or deny that at the moment.
And lastly, what is your geophone spacing must be pretty close if you're looking at these shallow depths.
Yeah, I mean, when we have, let's see, the examples I'm showing you here, the geophone spacing was 14 to 16 meters. Um, so pretty far. These have to be 60 channel, 120 channel systems that we use to get the array links that we need, to get the cross sections deep enough. Um, but that also means that the very shallow soils we're not assessing very well. Our information really starts at about 16 meters depth in this case.
I'm sorry, did you say 60 or 16?
16, 1 6. Yeah. We can see some of the shallow stratigraphy, but we're not getting a lot of detail. Not like not like a survey where the spacing is only 3 meters, which is what's typically done for the very shallowest.
Great, thank you.
Thank you. Okay, I have a question on the Q&A, um, uh, and it says, I'm curious, since it seems like repeat microgravity is popular for studies looking at aquifer storage and recovery projects, as well as groundwater depletion. Yes, indeed. Would repeat surveys with a shallow REMI array be precise enough to try and apply it in a similar manner? Um, okay, so we can certainly see this shallow. We are working on repeat and monitoring surveys. Consider the levee and embankment problem, or perhaps the earth and dam problem. If you do repeat REMI surveys, you could see any reduction in shear wave velocities that happens over time. And there are some clients of ours who are working on this. Now with deep REMI, if we're looking down at a kilometer, I think I would have to prove that we could do it. And so yeah, we're looking for a test bed. We'd love to try it, but I'd have to prove that we could do it. Okay. Next question: can Terēan tech possibly be useful for identifying or assessing lowering of the water table, like in the Central Valley of California? Yeah. In general, now Terēan includes we do P wave surveys, and we can help you do P wave surveys, and P wave surveys are a great way of getting the depth of the shallow water table. And the shallow water table tends not to appear in the shear wave results, which is good in one sense, that the shear wave results are not, they're not so dependent on the current state of the water table, like the P wave results, at least shallow, might be. But this is an interesting question. I'm aware that in Central California, in the Central Valley, there's been so much withdrawal that the porosity, of these deep aquifers is collapsing, and they're densifying, and that we should be able to see. So again, this is probably a really good candidate, in an environment like that where you get permanent change in the porosity due to withdrawal. It's also been mentioned to me that, and I think Gary Opliger, one of my colleagues at UNR, did some work on demonstrating that the shear wave velocity is an important parameter connecting the porosity reduction or the seasonal inflation and deflation of these basins, as water is injected and withdrawn. The shear wave velocity is actually an important parameter that connects the volume of water extracted or injected to the ground surface tilting and movement, vertical movement. So and what deep REMI does is measure the shear wave velocity. So that's another great idea that I would like to see proven. And we could sit down and Terēan is very interested in sitting down with agencies and operators and writing some proposals to see if we can get a study like this funded, maybe by other agencies. So these are very interesting research questions. Okay, and then I have a third question. How does REMI handle aquifer-specific material differences, such as clays versus the alluvial fill or clean sand? Have you seen this in any of the previous? And I think so, particularly here. What we're looking at is, the purple layer at the surface here in South Reno, in the Tumwa project, that is probably the most recent alluvium that we can see on the surface. And then we have a more gravel-rich layer B down below that. So yes, that kind of thing. The maximum grain size. I'm not saying you want to back that out of the velocity, but there is a correlation. So especially here where we can tie to the well, that's quite certain. And I think C is also more clay rich. So certainly in there's some really solid correlations to be drawn. And uh, as Tumwa and Terēan work on publishing this, yeah, send us your questions on it because we'd like to. These are issues that we want to address in our publications. Okay, that is all of the uh, that is all of the Q&A questions I have, and Peter Mock has raised his hand. Let me see if I can get to that.
Can you hear me, John?
Yes, I can. Try to speak a little bit louder, but I think I can hear you.
Yes, I'm impressed with the resolution, and from what I understand is basically background noise. Is that right? Did I hear that right?
That's correct. That's correct.
So my thought is, coming from a situation where we used to set off shotgun shells and things like that, could you bring in seriously a heavy diesel rig or a bass player and sharpen areas up along your lines if you need higher resolution? Would that help?
Well, I really like the bass player idea, um, and I had a thought when I did my original refraction microtremor work, way back when. Hey, maybe I should get a hip hop band and some jumping cars and all that sort of thing, and see what I could do with that. And it just turns out that in an urban environment, the it's so rich in this kind of background, seismic propagation that we really don't need to enhance it. We always enhance it uh, with an active source of some kind when we're working for code, building code classification, and uh, we have the building code to obey. We always do put in some hammer hits, but not like the active source surveys you've seen where it can take weeks to move your way down the profile. Um, so yeah, there are cases where some of these lonelier sites, you can imagine lonely sites in the middle of Nevada, on a day where it's not windy. Um, for really deep work, there's always the waves crashing on the coast of the Pacific. Um, and those waves actually get all the way through Nevada. It's been demonstrated by other seismologists. But yeah, in that critical, you know, 0.3 to 2 hertz band, where we're doing most of our work here, um, for deep REMI anyway. Um, yeah, we have um, some of our customers have weight drop machines. That of course requires a road. We found that if you record for long enough, if you don't just go out there and you record for several hours at least, then we can resolve the lack of seismic energy problem. Um, Eventually there will be a jet overflight or something that will light everything up in the right way.
Well, this is great. I didn't know that you could do things with the natural sources. It's fantastic. Thank you.
Yeah, it's really a great frontier in all of seismology right now, and you're going to see a lot of developments in a lot of seismological areas. Okay, Christian, yeah. Let me see if I can help you.
I got
Uh,
Tom. Can you hear me okay?
yes, I can.
Great presentation. Thanks for sharing. I wondered, we talked about this, I think, in other meetings, but I didn't see it in any of these slides, I don't think. Are you able to extend your fault traces to the surface? Have you seen that? And then, I guess if so, how do you do that? And then thirdly, is that, do you use that as any kind of evidence for being an active fault, for fault classification and for building design?
Right, right. Okay, let me first address the, extending to the surface. And you can see here that some of these traces at basin margins, I won't tell you where they are. Um, there's good evidence in the like at the upper left image, the two faults on the left side, um, and maybe the lower left image, the two faults in that. Uh, there is good evidence for those faults coming through to the surface. Yeah, also the one at the bottom of the valley on the lower right. So that which is the fault on the left of the lower right section. So those are ones where yes, we did see it clearly, um, and uh, now things are you come up into the upper 20, 30 meters here, and it's not as clear as it ought to be. Um, because this was a deep REMI survey, and in fact, you can see the station locations, which are the tiny white dots. Um, so how do you need to do a small scale survey, which again has the advantage that it only takes, it might only take you half an hour, okay, and as much more common equipment, um, and then you can get the surface resolution like this. Now, what can we tell about the fault? Um, well, we can tell where it's located. That's what we're getting from this image. Is the blue on the lower right here? Is that a colluvial wedge? From the last earthquake on the Calaveras Fault. Well, the Calaveras Fault it's a strike slip fault. It's a more complicated situation than the normal faults we tend to have in the basin and range. Um, but if you want to locate where this fault is exactly, and you want to assess what it's, when was the last event? Is it has it ruptured in the Quaternary at all? Then what the REMI survey helps you do is locate where you're going to trench or drill. And we have worked on uh, building projects, development projects in Las Vegas where we located faults. Some of them were located where the geologists had thought they ought to be, and some of them were not. Um, and uh, and then they knew where, they didn't have to drill the whole thing up. They could do many fewer drill holes and demonstrate where the faults were in the drill hole, and that's how they located the buildings of an apartment complex for one example. So yeah, it takes more work to you can't stop with REMI if you need to actually characterize the fault, what kind of earthquake can happen on it, all of that. Um, you've got to go into that paleoseismic trenching. In this case, on this property, um, the county was satisfied enough that they had located the fault well enough that they did not then need to engage in paleoseismic trenching. They said, all right, the geophysics shows where the fault is, and you're going to avoid that. They stayed more than 10 feet away from where the fault was, but they didn't have to stay out of the entire 100-foot wide Alquist Priola zone. So that's the advantage it had for this developer.
Kind of a follow-up, John, real quick. So was that then categorized as an active fault according to them?
Yes. I mean, everybody knew the Calaveras fault is active, so there was not that question at this locality. At the Las Vegas site, that was, of course, a big question. I mean, excuse me for saying it, but you can't spit in Nevada without hitting a fault. So, then the question becomes: is it important? Is the fault, worth avoiding? And that's really a different question. So far, what our clients have done is they've used the REMI cross sections to target their paleoseismic trenching, and they found that very effective and a big money saver. Okay.
One more, John. I'm sorry. Can I ask one more?
Yes, please.
Have you run these surveys across quaternary deposits where it's known that there are faults and see what that looks like?
That's the case in Las Vegas. We went across, one of our customers went across some faults mapped by DiPolo. They're really just in the Caliche and alluvium. We saw the sensible offsets in the caliche and the clay below that appeared very, very, very prominent in the shallow REMI result. And so we could find the faults there were cases where the faults were exactly where DiPolo mapped it, and there were cases where the fault was 100 meters away from where DiPolo mapped it. Maybe it was 100 feet. So then the developer took that information and did their drilling, that the county wanted them to do to show that they were missing the fault in the caliche and alluvium, with their building footprints.
And then they avoided that zone for building.
That's right. And now, we gave them the location of each fault to an accuracy of 30 feet in the case of that study, which I have reported at an AEG meeting, but we gotta work up a publication of this. The county required that you avoid the fault by 5 feet. Now that, to my geologist ears, I'm not even a structural geologist, but to the geology side of my brain, that just seems crazy. No way we could, you got to avoid the fault by more than 5 feet, but that's what the county wants. and they were able to confirm the location of the fault to within 5 feet with some drill holes. And I think, given the fact that there was a fault, that there were fault strands that offset caliche and clay below, that was enough evidence that the county needed to say, well, you have to avoid that fault. I don't think they collected a lot more evidence that it was those faults were active. So they're like many Nevada faults, they go once every 10,000 years maybe.
Do you have any other questions? Okay. Well, if you'd like to stay on the call, you are more than welcome to stay on if you have additional questions or information that you would like provided. But we are over your lunch hour, your time frame, 1 o'clock. So we'll let you go. Just as a reminder, we will send you an email following this webinar with an evaluation survey for you to complete and return. Please do so. We do appreciate it, as well as a certificate of attendance for your continuing education credits. Just a quick reminder that tonight we do have a networking social at the Village Well in Ranchera, and free drinks, food, and just kind of fun conversation. So if you'd like to join us, that starts at 5:30 and it ends at 7, but usually people stay afterwards. So thank you so much, Professor Louie, for joining us today and for your presentation. And if you don't have anything else, we can go ahead and let people off the call. And we do have a couple Q&A pop-ups here. So if you're available and can stay on the call, that would be great, but we'll let other people go if they'd like. Does that work? Okay. All right.
Thank you very much, Tina.
Oh my gosh, thank you.
I can stay a few more minutes.
Yeah, thank you. Sorry you didn't get to eat because you were talking. Hopefully everybody enjoyed their lunch and you were talking and you'll get to go eat lunch now. Let me just look at this Q&A box here and see if we have everyone accounted for. I think you probably did, and I just didn't click on the dismiss. No more hands.
I think, there were 3 in the Q&A and
Okay.
And I got them.
Okay, my box is smaller now that I've enlarged it. I can see that I think those are the 3 questions that you addressed. And does anybody have any other questions that's on the call? Alrighty, well, hopefully we'll see you tonight. And thank you again for presenting today. It's much appreciated. And thank Terēan. Is that how you say it? Terēan?
Yep, that's it. Yep.
Terēan, perfect. For sponsoring the webinar today, Spencer Fain and GeoExplore. So everybody have a really, really great day. And Joe Lysing, I noticed that you signed in a little bit later, and if you'd like to stay in the call, I can talk with you just to see if you have any questions. Let's see here. No?
Yeah, nice to see Joe.
Yeah. I'm sorry I missed it. I had a doctor's appointment that got changed this morning and a dental one, so I missed out.
There's a recording, Tina, right?
There will be a
Does that get
recording, in
posted
fact.
somewhere?
Yep, I am going to